Huw Morgan from Aberystwyth University for his generous support of the Zoom license we have been using for the UK-SOSS during the past 1 year. And today we are delighted to have Huw to deliver a talk on the characteristics of coronal streamers and resolving the line of sight with coronal rotational tomography. Huw, please.
Thank you, Jera. And regarding the paying for the Zoom license, it's very good quality for money, I think. This series has been great, and thank you for inviting me to give a talk today. So I have quite broad research interest, mainly focused on solar observational and data analysis. So the main focus of my work over the years has been to develop new methods to reveal new things in data. But today I'm talking about work based on coronal tomography, which has been my pet subject, or my obsession, if you wish, since the end of my PhD in 2005. So this talk is basically a summary of how recently the work has come to fruition after 16 years of effort. Okay, so I'll start off with a couple of slides of some scientific questions which I find particularly relevant. And my first question is which low atmospheric regions link to streamers and the slow wind? Or in other words, what are the sources of the slow solar wind? The only thing we can be totally certain about is that the fast, low density solar wind is coming from large coronal holes, usually the polar coronal holes. The slow solar wind has been shown to arise from the boundaries between active regions and nearby open field regions. So that's one source of the slow solar wind, but there are probably other sources. For example, we know we have two different types of streamers, and I've shown them in the bottom left here from Edwards et al. 2015. We've got a standard model of a helmet streamer where you've got a large system of closed magnetic field, and overarching these, you've got open field from neighboring regions of opposite sign, and you have a current sheet. Then you have pseudo streamers, which are, again, a system of closed loops, but the overarching field lines are of the same direction. So, and we know the slow solar wind coming from these two different types are different. Parker Solar Probe showed around 18 months ago that solar wind coming from a small equatorial coronal hole was of slow speed, but highly alphenic. So that's another different type of slow solar wind. I've talked about active region boundaries as a source. Is it possible also that the quiet sun, if the quiet sun closed field is next to open field, do we have a similar process there contributing to the slow wind? And another possible source of the slow solar wind is closed field region. So it's been shown above newly emerging active regions in particular, the closed field system above those can expand far out to at least 15 solar radii, which suggests that there is a quiescent mechanism for closed field from active regions to join the slow solar wind. So I'm mentioning here quiescent reconnection, and what I mean by this is reconnection not associated with coronal mass ejections or large large ejections. So at what range of spatial and temporal scales does this quiescent reconnection occur? And where does it occur? Active region boundaries, or more generally closed and open field boundaries, at the cusps of helmet streamers, and possibly others. Then looking more at this rather poorly defined boundary or transition from the corona to the solar wind, interplanetary solar wind. We're interested in the temporal variability of the slow solar wind. We know the slow solar wind is highly variable compared to the fast. But what are the components of this variability in the absence of large-scale features like CMEs? How and where do they form? How do they evolve? And a deeper question possibly, is the slow solar wind solely formed from blobby material, or is there a smoother background outflow on which the blobs are superimposed? Now linked to this temporal variability, of course, is the spatial variability. What is the spatial structure of the high density streamers, the streamer belt? Is it smooth, homogeneous, or highly filamentary? And studies in the last 10 years or so seem to suggest the latter, that the spatial structure is highly variable. A more basic question, what is the acceleration of the slow solar wind? And indeed, measurements of the outflow of the slow solar wind nearer to the sun in the inner corona is really highly uncertain. The error bars on the measurements are very large, and I'll come back to that later. And then, of course, the acceleration has even larger error bars. So this is a rather open question. And the last point I raise here, to what extent do different magnetic topologies, pseudo-streamers, streamers, etc., lead to different characteristics of outflow velocities, acceleration, composition, etc. To answer these questions, we've got two main sources of data. We've got in situ measurements, usually made far from the sun, and remote sensing, and by that I mean usually coronagraph images. The in situ measurements give very high sampling rates, very high precision measurements, and it's also a more or less direct observation of what you're trying to measure. So you're measuring the electron energy distribution, proton distribution, etc. But of course, the large downside to in situ measurements, you're measuring at only one point in space. So there's no large scale context of what you're measuring. So there's an interpretive uncertainty here. The coronagraph data has far lower sampling rates compared to in situ and large uncertainties. And of course, we're measuring light, which is not a direct measurement of a physical value. So there's a large interpretive uncertainty here, but we do gain information on broad regions of the corona. So we do have the large scale context. And to understand the coronal solar wind system, we need to really effectively link the in situ with the remote sensing. And to make further headway with interpreting the remote measurements, we really must resolve the line of sight. So what I mean by this, even if you have huge improvements in instrumentation, in resolution, signal to noise, calibration, etc., you still have this intrinsic line of sight uncertainty. So the corona is optically thin, as we know. On my cartoon here, we're looking down from the North Pole, if you wish, down through the corona. We've got a telescope here, which is measuring light. And at any single point in the corona, the visible emission is proportional to the electron density at that point through Thomson scattering. And then our measured light is the emission integrated along an extended line of sight. So here's a simplified version of the equation. The observed brightness is the line of sight integral of the electron density times this term G. And this term G has contains several constants and also geometrical terms. And I've plotted G here as a function along of distance along the line of sight. So I've done this for a height of 4 solar radii, and this point 0 is the point of the line of sight that comes closest to the sun. And this just illustrates that even though this G value is weighted towards the plane of the sky, it's very widely distributed along the line of sight, and this shows the line of sight problem. So if we observe, for example, a change over time in the brightness, we can never be exactly sure where that change is coming from along the line of sight. So how can we estimate density with this line of sight problem? Now, the most common approach over the years, in fact, over a century, using eclipse observations, is a simple inversion where you assume an underlying simple geometry to the density. So, for example, spherical symmetry, cylindrical symmetry, or just a local symmetry. And then you can invert the brightness directly to get density. Tomography, on the other hand, uses solar rotation to constrain the density structure. So we have approximately 27-day rotation period to the corona. And over that period, we assume the density is static. And we can then use the various views of the corona from different angles to constrain the density. So the motivation for tomography, the first motivation is probably the most important as far as society is concerned, and the practical side of it is as new empirical boundary conditions for solar wind models. So if we can achieve tomography at the height where the corona has become more or less radial, we're avoiding the complexity of the lower corona, and we can more effectively model the solar wind in interplanetary space. The results can be used to supplement or as a ground truth for coronal magnetic models. We can use for long-term studies of the structural evolution of the corona, which would be difficult to do otherwise. The densities we find put constraints on outflow velocity and acceleration. They're very useful for interpreting other types of observations, including in situ. And then a higher level method of time-dependent tomography can reveal temporal changes on smaller timescales. So in medical tomography, you have the luxury of being able to take hundreds of images all around whatever you're observing, so a person's head or a leg or whatever, hundreds of images within a short time period. And this enables rapid and robust reconstruction of the volume. In coronal tomography, of course, we have to wait for the sun or the corona to rotate. Since the corona is optically thin, we only need half a solar rotation. So around 14 days of data can give a reconstruction. We have to assume the density distribution is static over this period. So any CMEs or rapid changes will degrade the reconstruction process. So we have to have methods to reduce the signal of CMEs in the data. Another intrinsic problem is that the brightness drops very rapidly with height. So saved by a factor of 1,000 throughout your field of view. So even a very tiny error close to the sun is actually the same order as your actual measurement far from the sun. So this is a difficult problem. And of course, coronagraph data, there's noise, defects, missing data. And the largest chunk of missing data is, of course, hidden behind the sun or the occulter. And it has taken years of experiment to overcome these problems. So the method we developed a few years ago, I'm going to show data mainly from stereo core 2A. We can equally apply it to other coronagraphs, including LASCO C2. The core 2A coronagraph has an useful field of view between 3.5 to 12 solar radii. It's collecting data every 20 minutes to half an hour. We need precise calibration, and we've achieved this using thousands of stars observed in the field of view over around 8 years. We've developed methods to damp the signal coming from rapid changes such as CMEs, and a pile of other pre-processing and calibration routines published in 2015. To apply the tomography, we take a slice of the data at a constant distance from the sun. And we take slices over 14 days and stack them in time. So this gives us this type of data. And I'm calling this a sinogram to match what the medical tomography guys call their data. But this isn't quite the same cylindrical geometry as their sinogram, but it's very similar. So we've got time along the y-axis and the position angle measured from north along the x-axis. And we see a distribution here where we see the high density streamers, the bright streamers at equatorial regions in this case, and the darker coronal holes over the polar regions. Then rather than reconstructing density over a 3D volume, we collapse the radial dimension and we reconstruct over a thin spherical shell at a constant height. So the main assumption in doing this is that the density distribution is close to radial above 3 solar radii, which is a reasonable assumption. And we use a spherical harmonic basis for the density, which is a very efficient approach. So for example, on our spherical shell, say at 4 solar radii from the sun, we construct spherical harmonic based densities at different orders. So this is a low order on the left, going to higher orders. And then for each spherical harmonic order, we can do our line of sight integrations through these densities and create a brightness distribution or a sinogram for each spherical harmonic order. So I'm showing 2 examples here. So to do these line of sight integrations, we have to assume the density is radial above the height of interest. And we have to also assume that the density drops with a certain function of distance. And we use r to the power of minus 2.2. So r to the minus 2 would be mass flux constant. R to the minus 2.2 adds a little bit extra due to the solar wind acceleration. And then from all these brightness distributions based on spherical harmonics, we can combine them with different coefficients to create brightness distribution. So the problem becomes, the tomography problem becomes one least square problems without iteration, and the line of sight integrations only need to be done once at the start. So it's a very efficient approach. And I'm not going to go into more detail on the method. It's published in these two articles, where we create a synthetic corona, do synthetic observations, add noise, add missing data, and we test the method. And it seems to be a very robust method for reconstruction. So I'm showing a typical set of results here. This is in the ascending phase to the latest solar maximum. On the left, there are 5 density maps at heights between 4 and 8 solar radii. And just a few general points here. We seem to see 2 more or less symmetrical streamer belts at mid latitudes. The streamers can be very narrow in places. The structure at the 5 heights is very similar, so this proves the point that the corona is more or less radial at these kinds of these distances. And another interesting point is this very low density region between the streamers near the equator. And this right plot compares the sinogram of the observation, and also using this density distribution, what we observe from this model density distribution. So an interesting point here is that even quite a complicated distribution of brightness over time can be reconstructed using a static density distribution. So this complexity here you see of streamers seeming to split or join, crossing the pole, etc., can arise from a static density distribution. So this should be a movie, if I can get it to play. Okay. So we have created tomography reconstructions for every other day since 2007 at distances between 4 and 10 solar radii. This was done on supercomputing Wales. And this movie is showing the coronal structure between the minimum at 2009 to maximum at 2013. So, but just to be clear, each frame in this movie, each reconstruction is created from 2 weeks of data. So this is not time-dependent tomography, it's just a series of static tomographical reconstructions. So obviously, having the ability to do tomography on historical data like this is really revealing new stuff from the data, and it's almost like having access to a new instrument, looking at the 3D structure of the corona. When we compare the densities in the tomography maps with previously published values, so that the tomographical mean densities in streamers is shown as the black line here, and the dashed black lines are showing kind of the 5% minimum and maximum of values we find in the maps. And we get good agreement with previously published values. And the one difference with the tomography is we're showing that there's a large range surrounding that the mean value. And that was a value that was very difficult to do without tomography. And similarly for coronal holes. So the range of density is significantly higher than that estimated with simple inversions. And another surprising result was that when we look at the mean density of streamers during solar minimum, compare it to maximum, we find an almost identical profile with height. So there's no real difference in the densities of streamers at solar minimum and maximum. The only difference is at solar maximum, of course, the streamers appear at all latitudes, and the streamers also cover a larger area of the sphere. So the latitudinal distribution of streamers does not affect their global mean density. And this, since the density is related to the kinematics, the outflow velocity and the acceleration, this suggests that there's similar kinematics across the solar cycle, and in turn suggests that the same mechanisms driving the slow solar wind are unaffected by the different large-scale magnetic field structure over the solar cycle. These plots are concerned with mass flux. So the top plot is showing the total mass contained within a spherical shell of 1 centimeter thickness at these various distances from the sun. So at 4 solar radii, at solar maximum, the corona contains around 80 kilograms of plasma. So it weighs slightly less than I do. Quite a lot less than I do, to be honest. And if we look, the second plot down shows streamers. So we're isolating the streamers from the coronal holes. And what we notice is a drop in this mass over height, whereas coronal holes have more or less a similar mass at each height. And what this means, of course, is that the slow solar wind within streamers is accelerating at these heights, whereas in the coronal hole, the fast solar wind has already reached its nominal outflow velocity. So here I'm plotting, using those masses, I can calculate the ratio of the outflow velocity at a given height compared in comparison to that at the base height at 4 solar radii. And at solar maximum, we find that the velocity almost doubles between 4 and 8 solar radii, and also that there's a distinct difference between minimum and maximum. And to convert these into absolute velocities, we need an independent measurement. And luckily, Parker Solar Probe comes to the rescue. So in November 2018, Parker Solar Probe had a closest approach to the sun to date, and got within 35 solar radii of the sun. And this is showing the proton density measured by Parker Solar Probe during this perihelion, and also the proton outflow speed. This is a histogram of the proton flux. And we can use this outflow speed to map back from 35 solar radii back to the tomography height of 8 solar radii, for example. So this black, rather messy black line here with S for start, E for end, shows the path of Parker Solar Probe during this period. And of course, from Parker Solar Probe, we have the mass flux measurement we need, and we can then use the tomography and the Parker values to create an outflow velocity from the tomography maps. So the solid black line here shows the mean velocity from the tomography for these dates. And we've got large errors, and these errors are due to the variance of the mass flux measured by Parker Solar Probe over this period, plus the variance of densities within the tomography maps, plus other errors. The blue points here are estimates from the previous solar cycle for the slow solar wind from the ultraviolet coronagraph spectrometer on SOHO, Doppler dimming measurements. The range enclosed by the red lines here are estimates of the outflow of small-scale features in LASCO SOHO coronagraph measurements. And we see a good match between what we estimate from the tomography and Parker data at these kinds of heights, between 6 and 8 solar radii. Now, there seems to be disagreement with the Doppler dimming measurements from the previous solar cycle, but we can't really pin down more than that. It was a previous solar cycle, a different streamer. What the tomography does allow is a far broader range of measurements for outflow velocities, a far broader distance range. We get accelerations of around 6 meters a second squared at 4 solar radii, which drops off steadily. And comparing the outflow velocities we have with the outflow velocities measured by Parker, there should be a residual 1 to 2 meters a second squared acceleration, then further between 8 and around 30 solar radii. Notice the huge error bars, especially on the acceleration. It's the best we can currently do, but this does show a way forward. And the residual accelerations of 1 to 2 meters a second squared is a sensible value. We can use the tomography maps to compare with potential field source surface models of the coronal magnetic field. Now, these plots are taken from a previous study in 2010, and this was based on a previous tomography method I had, which was inferior to the current. But we can show that the potential field models do topologically agree with the structure, plasma structure we see in the tomography, but they do have inaccuracies in the position of these structures. So what I've shown in these right-hand plots is the current sheet or the neutral sheet in red, and then the black lines are showing the squashing factor or Q maps or convergence. I mean, there are 3 different terms for the same thing here. It's basically a measure of how widely separated field lines at the photosphere come to join a point in the corona. So regions where field lines have come from widely separated regions have a high Q value and expected to correspond to high density features. So, for example, we can see the streamer belt at solar minimum in 1996 splitting at this point, and we look at the potential field model, we get a similar splitting with a pseudo streamer, the high Q value in the south and the current sheet in the north. If we look at a more complicated example here from 1999, the tomography map is messy, the potential field map is messy, but the eye does see similarities. So we've got this very narrow high density streamer in the north corresponding to the neutral sheet here, the current sheet. We've got a pseudo streamer in the south, and indeed there is a density structure there. We've got this messy kind of oval shape in the tomography, in the plasma, and a similar shape in the potential field model. But notice that there's several tens of degrees of longitude or latitude difference in the position shown by the tomography and the potential field model. So the tomography can be used to highlight where the potential field model is in error. And this is something we hope to do quite a lot of work on in following years. Given the importance of potential field models, finally we have a way of showing how correct they are at the upper source surface height at 3 or 4 solar radii. These 4 maps on the left are separated by around 2 weeks. So we're moving forward in time from A to D, and by 2 weeks, 2 weeks, 2 weeks. And then what we notice is that structures, the high density streamers, are drifting in longitude. And we can take slices. So I've just shown as an example here a dotted white line. We can take slices at a constant latitude and stack these in time over the 13 years of results we have. This shows an example for the equator from 2007 to 2013. And what we notice are coherent drifts of streamers over many, many years. Now, at the start of the solar cycle, the years surrounding solar minimum, the drift is positive here in Carrington longitude, which means that the streamers are rotating faster than the Carrington rate. Then in 2009, possibly the start of the ascending phase towards solar maximum, we see a very abrupt change where the streamers have a negative gradient, which means they are now rotating slower than the Carrington rate. So tomography really is the only way currently to show this. Previous measurements of the coronal rotation rate would measure the brightness of the corona over several years and do an autocorrelation on those signals. But the tomography gives a finer time resolution on this type of result. And indeed, when we measure the gradients and the rotation rates of all these drifting streamers, when we average the rotation rates we get over many years, we get a result similar to previous studies, which shows a rigidly rotating corona. So this plot is showing latitude on the x-axis and the rotation rate in degrees per day as on the y-axis. And the red line is the average we get over all years for tomography. And when you compare that to the photospheric rotation rates shown here, the corona indeed looks as if it's rotating rigidly. But this hides the true nature of the coronal rotation. This lower plot is showing as a function of latitude and time from 2008 to 2020, the various rotation rates we measure. And these can vary from -2 to +2 degrees per day compared to the Carrington rotation. It just happens to be when you average them, that they average close to the Carrington rotation at all latitudes. So there's a real mixed bag here. And also we notice very abrupt changes. And this is something to do with the way the streamers are linked to the photosphere. So what I mean by that, at solar minimum, the foot points of the streamers come from mid-latitudes and curve downwards towards the equator. So when you're measuring the rotation rates in the corona for the equator, really the streamers are linked to mid-latitudes. And then with the ascending phase to solar maximum, there's an abrupt change in the configuration of the corona. We see this in the tomography maps and from images, where suddenly the equatorial streamer belt seems to split in two. And we believe this then, at the equator, you're measuring streamers that are linked closer to the equator. And then at higher latitude, you're suddenly measuring streamers that are linked radially to the mid-latitude. So it's a rather complicated picture which we are getting to grips with. But this work on rotation is very important, because if you have a corona which is rotating at a considerably different rate to the underlying chromosphere and photosphere, it means there must be interchange reconnection occurring. And also it has critical implications for solar wind modeling. Now, I've just looked at the time and realized I'm running behind. Very recent work, we're putting a time dependency into the method. I won't go into the details, other than to say it is working for times when there are not many CMEs. So this is an example for November 2018, where we can see the density changes in the streamer belt. And then looking more closely at points in the streamer belt and how the density changes over time, we get a very surprising result that there are huge variations in densities, factors of 2 or 3 increases in densities occurring at timescales of around 12 hours up to 2 or 3 days. Which of course makes us suspicious of the method, but it does match data very well. And also the time changes we impose are smooth. So smooth, slow density changes matches the data very well. And furthermore, when we compare with Parker Solar Probe data, so again, over November 2018, this is the proton density measured by Parker Solar Probe. And the lower plot here shows in black the time-dependent tomography density. The blue line is the static reconstruction. And we can see a fairly good correlation between the time-dependent tomography and Parker Solar Probe. So we do have confidence in this method. Furthermore, when we plot a density change over time at a point in the corona, and we do these for several heights and stack them like this, we find that differences in density, there's a lag between 4 and 8 solar radii, a consistent increasing lag. And this lag corresponds to a velocity of around 100 to 150 kilometers a second. So these are not CMEs. They're too large to be small-scale blobs or ejections. They are smooth changes in density, large changes in densities over timescales of 12 hours to 2 or 3 days. And this outward propagation speed can equally correspond to the plasma sound speed or the bulk outflow speed of the plasma. And we speculate whether they're caused by the motion of the magnetic field or changes in plasma density along the magnetic field, or both. And then finally, I am conscious of time here. We can use the tomography maps as a lower boundary condition for a solar wind model. So the results are very promising for this. We've used the tomography maps as a lower boundary condition for Reading, Matter-Owens at Reading's Hux-T solar wind model, and that is also working very well. And here are my conclusions. I'll allow you to read those in your own time. The ones highlighted in red are the more scientific results. We've got a new Leverhulme project to investigate the link between these tomography maps and the solar wind modeling. and also to include some CME studies. And we're also part of the STFC swimmer scheme to develop operational space weather forecasting for the Met Office. So thank you. Questions are welcome.